So this chapter is non-uniform learnability. So until now, we consider every hypothesis complexity are the same. The complexity of every hypothesis are the same. So the sample complexity or peng learning everywhere, we want to find out some sample low bound. After this amount of sampling, we can guarantee every single hypothesis. For instance, in uniform learning property, every single hypothesis can guarantee and the difference between training and test error is bounded by some epsilon with probability 1 minus delta. But in many cases in practice, we have different types of hypotheses. For instance, when we have this amount of data, so this is input, 1D input and 1D output, y, and continuous operable. And here we want to fitting this training data using function. So we can use a linear function, this is called linear regression, or we can use second order polynomial or third order polynomial, fourth order polynomial, and so on. And each function, what I just introduced, has different complexity. So maybe for this linear function, just 3 data points is enough to learn the best linear function. But for for instance, 10th order polynomial equation, just 3 data points is not enough at all. So we have to collect more data. So depend on which hypothesis we are considering, the sample complexity should be varied. Okay, so when we consider some hypothesis which is a joint set of many different type of hypotheses, then maybe some hypotheses belong to HI require 10 training data point, but some other hypothesis class require 100 data point and so on. So even for one single hypothesis class we are considering, each hypothesis can different. So each hypothesis require different numbers of training data point. That is called non-uniform learnability. So this is the definition of non-uniform learnability. Hypothesis class H is non-uniformly learnable if there exists a learning algorithm A and a function this which define the sample complexity. But when you look at this function, there are two types of input. One is for the target epsilon delta, and this one is for our hypothesis. So the sample complexity function and H null, non-uniform learning learnability, we also take into account the hypothesis. And then the output is the required number of training data points to guarantee epsilon delta. Then for every hypothesis, when we collect more than NH null epsilon delta H, then for every distribution D with the probability of n is 1 minus delta over the choice of training set at S, it holds that the rows of output algorithm for given training data point is less than or equal to the test error of our given hypothesis H plus epsilon. Okay, so when the number of training data point is more than this, then we don't need to worry about this specific hypothesis and most epsilon amount. So what is the difference between non-uniform learnability and packed learnability we studied last time? So this is the definition 3.3 we already discussed. A hypothesis class H is agnostically packed learnable if there exists a learning algorithm A and a function N, which again define the sample complexity for any given epsilon and delta, which make output integer number that define the sample complexity. If n, the number of samples, more than nh epsilon delta, then for every distribution D with probability of n is 1 minus delta of the choice of training data, it holds that this. Okay? The only difference thing is the sample complexity does not depend on hypothesis class. Okay? So NH epsilon delta samples can guarantee at most epsilon additional error for all hypotheses, but the non-uniform learnability NHNU L epsilon delta H, which is only for a specific hypothesis H, right? So agnostic packed learnability is more strict condition. So when we have agnostic packed learnability result, then naturally the hypothesis class is also non-uniformly learnable with this sample complexity function.